So when you go to a baseball game, you're allowed to have a seventh inning stretch, and even though we're about a minute behind, I want everybody to stand up for 1 minute and take a stretch because it's been too long. I'm not going to lead you and take me out to the ball game, however. Okay, now I'll put you back to sleep now that So thanks very much for having me here today. I have quite a number of slides, so I'm going to jump right into it here. I'm asked to talk about technological challenges and opportunities within desalination. I'm going to focus on inland desalination. If I can figure out how to use this thing. Oh, here we go. Okay. So, you know, when I go to a party or talking to people that are not in our field and they find out what I do and they, you know, these days it's almost inevitable they ask, you know, is desalination possible? And I said, of course desalination is possible. You know, we're doing it and we're doing it in a substantial way. And, you know, so I kind of make it sound like desalination is simple. And this is kind of the picture they probably have in mind, except they probably don't even realize there is a concentrate. They just think, well, you take salty water and make it into clean water and all's well. But in fact, desalination is not so simple as everybody, I think, in this room knows. And you know, I think there's 4 areas in which desalination is not so simple. And the first one is the desalination process itself. And the second one is that there's actually quite a bit of pretreatment that we often have to do before we get to reverse osmosis membranes, and so you know, there's pretreatment issues to be concerned about. And then there's post-treatment, which we often don't think about, but desalination or, you know, RO water is sometimes so clean that it's not good for what we want to use it for, and we have to add things back into it. So we have post-treatment issues to concern about. And then we have the issues of concentrate management, which Ed just mentioned, and are a critical part of things. I've done a fair amount of research on some of these things, particularly on the pretreatment and concentrate management, and I'm going to comment on all of these, but I'm going to focus on those 2, and hopefully not bore you with a few of the research results that we've had in our work here at UT Austin. So, you know, with respect to the desalination itself, you know, to me, the heart of the nexus of energy and water is the thermodynamic limits for how much energy you have to spend, just as an absolute limit because of the science in desalination. And, you know, there's been absolutely enormous strides in trying to get down to that energy, that level of energy use in desalting water. And a lot of that's had to do with the fact that there's been a lot of development of the membranes. And there's also been pretty remarkable progress with respect to pressure recovery, especially in seawater desalination. And there's probably some room left for more progress in that area, in both of those areas. And, you know, those things I think are going on at a number of places around the state and around the country and around the world. The development of new membranes is something that our chemical engineers in my department here at UT are involved with. And the pressure recovery is really a mechanical engineering issue. And again, I think there's some progress to be made there, but I'm not going to focus on it because I don't do that kind of work. Pretreatment, I think, that represents some very interesting challenges and perhaps some opportunities. We have to worry about biofouling control on the membranes, and so oftentimes we do that by chlorine disinfection, and if we do that, we either have to dechlorinate after we chlorinate, or else we have to develop some chlorine-resistant membranes, and I think that there's definitely some opportunities for improvement in that regard. Ozone is a very popular way to do disinfection, but if you have bromide in your water, you end up forming bromate, which does not get captured in RO membranes very well, and so you end up having water quality problems if this is a drinking water source that you have there. Another area is just particle removal. Very few waters are perfectly clean with respect to particles, and oftentimes pretreatment has to use conventional drinking water treatment processes, coagulation, and oftentimes ultrafiltration membranes to prepare the water for RO. And then a big issue with respect to reverse osmosis membranes is scaling control. And so we oftentimes reduce the pH of the water so that we don't precipitate a whole variety of different kinds of solids that on the membranes as we increase the concentration of the ions on the pressure side of the membrane. We often add organic antiscalants to do that in addition to acid addition. And then I particularly note silica control because silica oftentimes is the critical component that prevents us from increasing the output from desalination membranes. And I actually had a PhD student a few years ago who did some work on that. I'm going to just show you a few of the slides just to give you an indication of the kinds of things that are done. This water that we were using was from the Rio Grande. Near and dear to Ed's heart. This was actually from much farther southwest along the river, but in any case, this is a composition of the Rio Grande water, and it has a very high silica concentration in here. Also has calcium, magnesium, alkalinity that are important to be concerned about. And so what Rocio Pacheco did was a lot of experiments and some mathematical modeling. This is the mathematical modeling that shows that if you add a lot of lime, which is on the abscissa of this graph here, you can reduce the concentrations of pretty much all of the bad actors, silica, calcium, and magnesium. But it takes a lot of lime to do that. You can see this bottoms out here around 170 milligrams per liter of lime, which is substantial. And when we do softening plants for surface waters to reduce calcium and magnesium, we use doses that are maybe not quite that high, but are in the same ballpark. She also did experiments, and again, I'm not going to go through the details of this because I don't think that's the main point here. But what is the point is that she could reduce the silica concentrations rather dramatically by this chemical pretreatment prior to membranes. And then she kind of used a few different levels of pretreatment. You can see these levels are given here as calcium, magnesium, and soda ash being added in here. They're not tremendously different, but the results were interestingly different with respect to the silica, magnesium, and calcium concentrations that could be achieved. But you see that you had to operate at high pH to do that, and then prior to going into an RO membrane, you'd have to reduce the pH. And so she did actually RO experiments. And on the graph here at the top, I'm showing how the flux changed as a function of how much water you put through the membrane in a normalized way. So this could be compared to what would happen in a real system. And it turns out that this first pretreatment resulted in far less flux reduction, which really means much less pressure use and more water recovered coming out of the membrane. So again, the details aren't critical to you here, but the point is that with pretreatment, you can make tremendous differences in how much water you get out of the membrane. Of course, it costs you money to do that, and so it's a trade-off. Do you get a dollar value out of this sort of pretreatment? And the answer is oftentimes yes, if you can make this kind of difference. And then another area has to do with post-desalination water treatment. And oftentimes, RO pretty much takes everything out of the water. I mean, that's a slight overstatement because some ions and molecules do make it through RO membranes. It's a huge issue in the chip manufacturing business that low molecular weight organics do make it through membranes, and in that industry they need super high quality water, and if there is any low molecular weight organics in the water, that they can really wreak havoc on their product. But for the most part, RO takes out almost everything, And it turns out that we don't want to drink water that has nothing but water in it. And so we need to add things back in. And also that water can be too corrosive for piping. So we have to add minerals back in, for example. We have to add carbonate back in so that the water is pH adjusted and doesn't change dramatically. It's possible to provide those by putting some of the chemicals that you took out in RO back in by blending in a little bit of the concentrate. But you have to worry about whether that works for your water quality. In some cases, it turns out that hydrogen sulfide also can make its way through RO membranes relatively easily, and so sometimes if you have sulfide in your groundwater system, you may have to strip the hydrogen sulfide afterwards. Hydrogen sulfide is what tastes like rotten eggs, and so a very small amount will lead to lots of complaints from your citizens if you supply them that as drinking water. You often have to add, because of corrosion control, you have to add polyphosphonates back into the water. And of course, you have to make sure the water is disinfected, and you provide, at least in the United States, we always provide a residual disinfectant in the water. And so all of these things represent costs and energy being spent to make the water useful even after you've taken all the salts out. So to me, there's a lot of challenges here and not many opportunities. I don't think there's a whole lot that can be done about this. You can maybe work on ways to make it cheaper, but in essence, these things pretty much have to happen for most water uses that we're going to do, and I think it's oftentimes not thought about very much. The big one to me is concentrate management. Ed mentioned this as well. He pointed out they're pumping their concentrate 22 miles or something like that to put it into groundwater re-injection. What happens is that we have to worry about that. And I've used this slide because I want to emphasize that the product, if it's drinking water, is some percentage of the feed water, and the concentrate is the rest of the percentage. And so if there's anything we can do to reduce the amount of concentrate, we're going to increase the amount of product water or drinking water we have there. And my research over the last few years has focused on this. And I'm going to, here's talking about recovery is the way to do that. The fraction of the influent water that you get to use as your final product water is referred to as the recovery. And the higher the recovery that you have, then the less concentrate that you have. And I think that's one of the goals that I have. So in the work that we've done, again, we're particularly looking at inland desalination, where concentrate disposal, to me, is the predominant challenge. In seawater desalination, as Ralph pointed out a few talks ago, you can put the brine back into the sea, and as long as you are not careful about how you do it, there doesn't seem to be any significant effects. But in inland desalination, concentrate disposal is expensive. It has potential ecological issues associated with it, and so to me, it's the primary challenge that we face. So a typical RO plant looks like this. In inland desalination, you put RO units in series, and you take the concentrate from one and use it as the feed to the other. But eventually, you get to the point where you're going to have scaling going on the RO membrane, and you can't go any farther, and so you stop. But the work that we've done is to look at other processes that we can put and deal with that what would now be the concentrate. And one of those is electrodialysis that you could put in line here and do that. And the other one is to do a much more complicated system, is to, and it's shown on the bottom here, to take the concentrate from your final RO unit and do an antiscalant oxidation, perhaps or perhaps not, then do a precipitation process, because the reason why you've had to stop your RO process at that point is because you're worried about precipitation onto the membranes. And then if you do the precipitation and create new solids, you do a solid-liquid separation, and then you can maybe put that liquid part of that back into another RO unit. And the whole idea of both of these things is to increase the amount of product water and decrease the amount of concentrate that you have. And because concentrate disposal can be expensive, turns out you can spend a fair amount of money on this and still have it be worthwhile. I'm not going to go into the details of this. It would take me several slides to explain all of this. I just chose a couple of the slides as part of the explanation of this. This is the work of Lauren Greenlee about antiscalant oxidation as the a step before precipitation. And she was using, as people do in the field, a phosphonate antiscalant. And by using peroxone, the combination of hydrogen peroxide and ozone, you could oxidize that, and the oxidation is shown by the amount of phosphorus that's on the ordinate here. And basically what she discovered is that when you had calcium in the water, you got a lot more of this than when you didn't have calcium in the water. And then the question was, why? And again, the technological details aren't important to you. The point I want to make is that these are the kinds of difficult issues that take a lot of research to solve, but they are solvable, we can learn a lot from this sort of thing. So what she discovered, in essence, was that there were complexes formed between the antiscalant, which is this DQ 2006 here, and calcium, that had a speciation that was a function of pH, and that one of those seemed to be the critical player in allowing the ozonation and peroxone to actually destroy the antiscalant. And so this kind of graph indicates that when you didn't have any calcium in the water, down in the low graph here, you didn't get much oxidation at all, but when you did have calcium in the water, you had, as a function of pH here, substantial amount. And again, that graph has the same shape as the one species. Again, those details are not critical to you. The point is that research can solve these problems for this kind of work. Just to show you that that sort of work then can result in increased use of the increased recovery and reduced concentrate to get rid of, the effect of the various amount of ozonation is shown on this graph here, and the dotted line near the bottom is basically what happens if you don't have any of these problems in there, and then if you use the antiscalant, you can get more. But basically, we're trying to get back down to this level here, and what this shows is that the treatment, if you have enough ozonation going on, that you can destroy the antiscalant and therefore get the precipitation to happen to a great degree, and that gives you then cleaner water that you can put onto another membrane. I'm not going to bother with this slide. I think it basically just shows why this works, why this next slide happens, but what happened again now, so she went to do ultrafiltration membrane to get as the solid liquid separation device, and again, a high flux is a good thing here, and a substantial flux decline is bad, and you can see that without the addition of the ozone, that you got a substantial flux decline, whereas with the ozone and the antiscalant, you basically got the same thing as if you had no antiscalant at all, which meant that the process of antiscalant oxidation worked, and that you could then get good removal in a subsequent reverse osmosis system. And this graph just tries to indicate that what would happen with that sort of treatment is that you could increase the amount of recovery that you get from your inland desalination system relatively substantially. And just an increase from, say, 85%, I think Ed said they got 83% in their system. If you can increase the result from 83% to, say, 90%, which doesn't sound like it's tremendously dramatic, what you've done is you've changed the amount of concentrate from 17% down to 10%, and that's a huge difference in terms of the cost that you have to spend for disposal. So small, relative, what sounds like small increases in recovery lead to large savings in concentrate disposal. The second way that we've looked at this is to use electrodialysis, and I'm not going to go through all this in detail, but basically the concept is that you provide all these membranes, anion exchange membranes and cation exchange membranes in alternating pairs, and you provide an electrical voltage from one side to the other, and ions can't move towards, can't, like an anion can't go through a cation exchange membrane, and so it is blocked, and it's vice versa for cation. And whereas if the particle or ions come through the other systems, they can go through the membranes on either side, and you end up with clean water coming out every other pair, and that's called the diluate. And you have dirty water coming out the other pairs, and that's called the concentrate. So you basically can make this ion separation in electrodialysis, which prior to the development of RO membranes getting so much cheaper, electrodialysis was used for desalination, but it was pretty expensive to do. So there's a current that runs through there, and so Shane Walker, who was mentioned earlier, who was a PhD student of mine who did this work and is now a professor at UTEP and is in the room somewhere, developed this system. And at the center here we have this small electrodialysis system, and a diluate reservoir and a concentrate reservoir, and you need to use an electrode rinse because there's gases formed at both the electrodes that you have to get rid of. And in a real system you may have 100 of these pairs or 200 pairs. In our system we had just 10. And of course, because this is research, we had to monitor all the flow rates and all of the pumps that were on in there, and we had to measure the pH and the conductivity and the temperature. And when we put it all together, it looked like this. And this massive system here, which Shane is laughing, I can hear him. So somewhere in here, this tiny little thing here is the electrodialysis unit, and everything else is to make it all work. But in any case, this is the research system that he used. And the point of it is that we were dealing with basically concentrate from an RO system. So we assumed there was going to be 80% recovery, and so we made up these waters at 5 times the concentration of everything else. And basically this shows that it works. And it works different the more voltage that you put on in there. So let me try to wrap this thing up because I'm getting signals that tell me it's time. So I have a slide for each of the 4 things that I said here. Desalination itself can now be considered a relatively straightforward process. I believe that that is true. There are remaining technological challenges and opportunities, improving the membranes, as I mentioned, increasing the specific flux with the membranes. That means the flux per unit pressure that you do in here. And I think that there is improvement to be made there, although there have been tremendous advances. Pretreatment, I think, has many technological challenges. The site-specific problems require a lot of creativity in solving them. Certain chemicals are frequently present and particularly problematic. Silica, boron, bromide are ones that I'm kind of conscious of. Compatibility of biofouling control options with subsequent desalination process requires a difficult balance. I think that there's many opportunities for improved recovery here. If you do the pretreatment right, you can get much better recovery, and that's very useful. Post-treatment is generally straightforward but must be done with care. I don't think there's a lot of opportunities for improvement. Well, it has lots of challenges and really few opportunities for improvement. And lastly, I think for inland desalination, concentrate management is the biggest challenge and also the greatest opportunity. Treatment of the concentrate to improve overall recovery is the most promising option. For example, electrodialysis or precipitation with further RO treatment, but it requires continued research and probably somewhat site-specific research. Many current, quote, solutions appear to me to be ecologically unwise. Deep well injection, land disposal, sewer disposal, I think all of those ultimately have problems that we should try to avoid. Zero liquid discharge is something that's talked about. It's probably technically infeasible. But I think we should think about it as a goal because it's just kind of like it's always out there for us to improve. And finally, thanks to my PhD students who do all the work and the funding sources that supplied the money for us to be able to support them while they did that work. Thank you very much.